In this video, I want to talk about a specific type of problem that we can solve using linear algebra, which is known as a Markov chain. I'm going to give you an example of Markov chains. I'm not going to fully solve the problem that I present, but I'll give you a sense for what's going on. And hopefully I'll also give you an idea for how many different applications there are where Markov chains would be useful, and also an idea of what sorts of things we're going to do with these types of problems. The goal of this video is to get familiar with the idea of Markov chains and how they're useful. And in a later video, I'll go through all of the different calculations in detail. So let's start with our example. Suppose we have three internet service providers in a city. So providers A, B, and C. And every year people switch between them at the following rates. And so just a quick side note, if this seems unrealistic or contrived, you obviously haven't had to be in charge of your own internet, because I can personally say that I have switched internet service providers so many times and I've gone back and forth between the same ones based on quality of service, discounts that they offer, and things like that. So I think this is actually realistic that this sort of thing happens. And let's say that the rate at which they're switching, if you start the year with provider A, there's a 5% chance you'll switch to B, a 15% chance you'll switch to C, and that leaves an 80% chance you'll stay with A. And similarly, if you start with B, there's a 10% chance you'll go to A, a 20% chance you'll go to C, a 70% chance you'll stay with B, and similar for C, we have rates at which people are switching. Okay, and let's also say that right now, 20% of the town is using A, 20% of the town is using B, and 60% of the town is using C. My question is, what about next year? What percentage are going to be using each service? And this is actually not that hard to calculate, right? So we can figure out what happens to all of the people who started with A. So 20% started with A, and 80% of them will stay with A. So that's 16% of the people. And 20% of A, of them, 5% will switch to B. That's 1% of the people in the town. And finally, of that 20%, 15% go to C. That's 3% of the people in the town. And this adds up to the initial 20%. And we can do the same thing for B. We can figure out, of that initial 20%, how many end up in A and how much does that add up to for the whole town. And we can do the same for C. Figure out of, the 60% with C, how many end up at A, how many end up at B, how many end up at C. And if you're not sure where these numbers come from, just pause the video, think about it. I'm rushing through it because I don't want to dwell on these smaller calculations. And then we add all this up and we realize, okay, well, we have an answer to our question. We end up with 36% with service A, 27% with B, and 37% with service provider C. Okay, so nothing really linear algebra yet, or maybe you're seeing it, but I don't think it's obvious. So the problem with what I've just done, with viewing this problem as just a brute force calculation, is that there's natural questions. We have some natural questions that we don't want to have to brute force. Like, for instance, if you're working for one of these companies, right, and you know this, you might wonder, well, okay, fine, that's what's going to happen next year, but what's going to happen in 10 years? I could do this by brute force. I could do this 9 more times, but I don't want to, right? And then you might go even further. You might have a really long-term view. You might say, what about long-term? Will this eventually stabilize? That is, you'd still have people switching around, but maybe you hit some sort of stable point where even though people are switching, you start with the same percentage that you end with, right? It just kind of all evens out in the end. And these are, I think, natural questions to ask. And it turns out that in order to answer these questions in a nice way, we need to think about this problem in terms of linear algebra. Now, I said you may have noticed this or you may have not noticed this, but one of the things that jumps out to me as linear algebra from this, when I look at this problem, is that I'm seeing kind of numbers multiplied by each other, and then the corresponding results, some of them getting added together. And that jumps out to me as something that looks a bit like matrix multiplication, right? Where we do some multiplications and then we add them together. And if you reason it out in this problem, you realize you can model this with a matrix. And so what matrix can you model this with? Well, I'll show you the matrix, and then once you see it, I mean, you'll immediately know where the numbers are from, and you can convince yourself that it's correct once you have it. So the first column is going to represent where people from ISP-A switch, or the rate at which they switch services. The second column represents where people from ISP-B switch, and the third column represents where people from ISP-C switch to. And the idea is that this is, let's write this in different colors. This column represents where you start, A, B, and C, and the rows represent where you finish. Right? So someone who starts with ISP-C, there's a 30% chance that the next year they'll be at ISP-A. And once you do this, you realize that you can just calculate what we did using a matrix multiplication. I don't know why I wrote A equals. If we multiply this by the initial if we multiply this by the initial distribution, right? So we started with 20% A, 20% B, and 60% C. We get exactly these numbers. And the reason we get them is the calculation is the same thing. You can follow through and see that it's just exactly what we did, written out as matrix multiplication. So we haven't even saved computational time, but by viewing it this way, we're going to be able to answer these sorts of questions really nicely. If we want to know what happens in 10 years, if we introduce this into software, what we can do is we can take this matrix and we can raise it to the 10th power and then multiply by this, right? So we have a nice structure for doing this calculation. And we'll see that in terms of this long-term behavior question, this is going to be related to eigenvalues and eigenvectors. And so we'll eventually find that in the long run, 50% of people will end up with service provider A, 25% will end up with service provider B, and 25% will end up with service provider C. And kind of crazily enough, that's independent of where we started. Even if everyone started with service provider C and all of a sudden these other two service providers came to town, you would end up with that same stable solution. So I've talked about in this specific problem kind of what we'll try to solve, but more generally, what about this problem makes it a Markov chain problem? And because that'll let us know what other kinds of problems we could encounter. So what's special about Markov chains? I don't know why let's move this out of the way so that we don't have to focus on it right now. A Markov chain, what's important about this problem is that we have a fixed number of states that we can be in. In this case, you either have ISP-A, ISP-B, or ISP-C. I didn't have the option of no internet. Maybe I should have done that because to me that's crazy, but I know that some people might want that. And at each time step, in our problem, each time step is a year, there is an associated proportion or probability for each state. So our initial situation, our associated proportion or probability was we started with 20% in A, 20% in B, and 60% in C. And then at the next time step, we had an associated proportion or probability or percentage with 36% in A, 27% in B, and 37% in C. So we have these states, and at each time step, some percentage or proportion will be in each state. We can think of that as a probability. And then the really important detail here is that, or property is that the likelihood of switching from one state to another depends only on the current state. Right, so here I said, where you end up next year, the ISP you have, depends only on where you are right now. So if you have ISP A, the chance that you're with ISP A next year is 80%. And what this is saying is, this is where my example is maybe somewhat unrealistic. We don't need to look back to previous states. So let's say 2 years ago you had provider A and they were terrible. The service was awful, and so you switched to provider B. This is saying that it's somewhat memoryless, in that what's going to happen the next year doesn't matter whether you switch to B from A or whether you switch to B from C. And that's probably unrealistic, right? I think that in the real world, if you were switching around between different providers, you would probably think back to past your current one. But lots of problems, it's realistic to model where it's somewhat memoryless. That is, your current state is all that determines your next state. So that's what's important here. That's the sort of problem that we'll be able to solve. Fixed number of states. At each time step, there's a probability that you're in each state, and your likelihood of switching at the next time step only depends on your current state. What other sorts of problems can be solved using this? We talked about switching internet service providers, movement of populations, right? People moving from towns to towns, states to states can be modeled by Markov chains. Financial markets can be modeled by Markov chains. There are so many things that can be modeled at least approximately by Markov chains. And so it's a worthwhile thing to understand and to try to study. The final thing I want to talk about is this matrix we ended up with. It's matrix A. This matrix has some special properties, the first two of which are relatively obvious from our context, but I'll still mention them. The columns add up to 1, and the entries are non-negative. Going back to our matrix, this is saying if you start with provider A, everyone is going to go to some other provider, or maybe stay in the same place, right? The total probability is 1. That's a reasonable thing in lots of situations that you're modeling. Why do these have to be non-negative? Well, probabilities have to be between 0 and 1, right? You can't have a negative probability. So if we're thinking of these as measuring probabilities or proportions of the whole, these two probabilities I think are totally reasonable. So the columns add to 1 and the entries are non-negative. But there's this other property that is not at all obvious. You always get an eigenvalue of 1, which is not at all obvious, but you always do. There's always going to be an eigenvalue of 1. And what this means in the context of the question is that this corresponds to a steady state solution. And what I mean there is if I take this matrix A and I multiply it by the steady state solution that I claimed without proof, you can do this on your own if you want to confirm this, you just get back what you started with. So if this is an example of an eigenvector of A with eigenvalue 1, and this is saying in the problem context, if half of the people are using service A, a quarter are using service B, a quarter are using service C, they'll switch around for the next year, but they'll end up in the same proportion as they were beforehand. And again, why this is true is a bit mysterious. It's not crazy, and I'll probably talk about it at the end of this later video where I do problems, but I think that's a good place to leave this. So hopefully you have an understanding of what a Markov chain is, how widely applicable it is, and some of the things that we can do with Markov chains.